section 3.8. Please take a look at this. Let us consider a linear operator from R2 to R2, which is given by this formula. T of x is equal to ax, where a is this. We have three inputs, x1, x2, x3, three vectors. Find t of x1, t of x2, t of x3. In order to solve this problem, we replace a by this and then x by x1, x2, x3. It's exactly what is done here. And then multiply each vector by the given matrix A from the left. But now, please take a look at this. Observe that t of x1 is equal to x1. T of x2 is equal to 5 times x2. And now, if you compare t of x3 and x3, there is no obvious relationship. So, this linear operator t satisfies the following property. T of x1 or t of x2 is a multiple of x1 or x2. T of x1 is a lambda x1 and t of x2 is a lambda x2. In case number one, a lambda is 1. In case number 2, a lambda is 5. In the next exercise, again, t is given, a is given. We want to find not just 1 or 2, but all numbers lambda and all non-zero vectors x such that t of x is equal to lambda x. Take your time, think about questions.
So what happens with x3 since there's no like obvious rule?
Well, nothing. It just, you see, I gave you this example as an illustration.
Oh, okay.
For some square matrices, when we multiply some vectors by these matrices from the left, the output is a lambda times input. This is what I'm trying to say.
Okay, cool.
So let us continue. Once again, in this problem, we are trying to find all solutions of the following equation. Ax is equal to lambda x. Moreover, and this is, guys, important, please highlight this word, non-zero. Here's why we care about non-zero vectors. Note that if x is a zero vector, then ax is equal to a lambda x for any number lambda. Therefore, from the very beginning, let us exclude this trivial case. We want to find all non-zero vectors such that ax is equal to lambda x. And here's how we do it. In a moment, I'll show you that the equation ax is equal to lambda x can be rewritten as a minus a lambda I times x is equal to 0. Why is that? Well, here's work. So once again, we start with our equation ax is equal to lambda x. Observe that if we move lambda x to the left, we will get this. And now, looking at line number 2, we see that x is a common term. Our natural intention is to factor out x. However, we cannot do it yet. Because if you factor out x in parentheses, you will get a minus lambda, which is an absurd. We cannot subtract a number from a matrix. Now, you may ask me a question, how come that we cannot really factor a common term? Because we know that matrices enjoy distribution property. Let me go back to section 3.6 and please take a look at this. Matrices do enjoy distribution property. Well, unfortunately, in line number 2, we cannot apply distribution property yet, because if you take a close look at AC, in order to apply distribution properties, all three, A, B, and C, should be matrices. Observe that in line number 2, A is a matrix, X is a matrix, but lambda is not a matrix. Therefore, right now, we cannot apply distribution property. However, it is easy to fix this problem, because note that X can be rewritten as Ix, where I is the identity matrix. Remember, multiplication by the identity matrix does not change anything. And now, in line number 3, A is a matrix, X is a matrix, a lambda I is a matrix, X is a matrix. Now we can use distribution property. We factor out X and the result follows. Folks, any questions here?
Wait, how did we know that in the beginning lambda is a number and not a matrix?
Because it's written.
Okay, it's written.
All numbers a lambda.
Okay.
Here's what we do next. Let us denote A minus lambda I, and remember A minus lambda I is a matrix. Let us denote A minus lambda I by, say, B. If we denote A minus lambda I by B, we will get this. And note that Bx is equal to 0 is a homogeneous system. But remember, we want to find all non-zero vectors that satisfy this. And as we discussed, this question can be translated into the following question. Find all non-zero solutions of this homogeneous system. And now, let us go back to this corollary. This corollary says that a homogeneous system has a non-trivial, non-zero solution if and only if its determinant is equal to 0. Conclusion: determinant of B is equal to 0. And since B is A minus lambda I, determinant of A minus lambda I is equal to 0. Going back to our matrix, remember our matrix A is 3, negative 2, 1, 0. Therefore, A minus lambda I will be this minus lambda times I. We move lambda inside, done. We subtract corresponding entries, and here's matrix A minus lambda I. We find its determinant. Determinant of this matrix is this, which can be rewritten as this. Therefore, the only two values for which t of x is equal to lambda x is a lambda is equal to 1 and lambda is equal to 2. We solved 50% of our problem. We found lambdas, all lambdas, for which T of x is equal to lambda x. But then how do we find vectors? Well, remember, vectors that we need are non-trivial solutions of this homogeneous system. Therefore, in order to find all non-zero vectors that satisfy this, we have to find all solutions of this homogeneous system. It's exactly what we do here. Suppose lambda is equal to 1. It's case 1. In order to solve our homogeneous system, we create the corresponding augmented matrix and then apply elementary row operations to come up with a reduced echelon form. Which means we replace first a lambda by 1, done. We switch positions, done. And then subtract row number 1 multiplied by 2 from row number 2. Here's the reduced echelon form. After that, we write down the corresponding system. In our case, it's just a single equation. We move the free variable to the right, and then x is equal to x2 times 1, 1. Here's a complete description of vectors x that satisfy the following equation. Tx is equal to 1 times x. For lambda is equal to 2, we apply same idea. Here's augmented matrix, which can be rewritten as this. If lambda is equal to 2, we subtract row number 1 from row number 2 to obtain the reduced echelon form. Here's our equation. We move 2x to the right, and here is a complete description of all vectors such that t of x is equal to 2x. We summarize all these results over here. Guys, any questions?
How did you know that x1 was a free variable?
Well, how do we know which variable is free, which variable is basic? We look at columns. If we have a pivot column, the corresponding variable is basic variable. If we have a non-pivot column, the corresponding variable is a free variable. Note that in this matrix, column number 1 is pivot column, therefore x1 is basic variable, we leave it on the left. Column number 2 is non-pivot column, therefore x2 is free variable, we move it to the right. Does this answer your question?
Yes, thank you.
Other questions?
So why would it be wrong to, let's just say, instead of saying x equals x2 times the matrix of 2, 1, why would it be wrong to say x equals x1 and then the matrix 1, 1/2 or something like that?
It is not wrong if you rewrite x2 as 1/2 x1. Then over here we'll get x1, 1/2 x1, and if you factor out 1/2, we'll get 1, 1/2, which is same because x2 is any non-zero number. Does this answer your question?
Yeah, it does. So like when we present our answer, it can be in terms of x2 or x1.
Absolutely, but I'm applying standard procedures.
Right, that makes sense.
Now let us talk about terminology. A non-zero solution of this equation is called an eigenvector. Important, guys. 0 is not an eigenvector. An eigenvector is only a non-zero solution. And then a lambda, for which this equation has a non-zero solution, is called eigenvalue. Lastly, and this is kind of confusing, the eigenspace of A is not a collection of eigenvectors only. The eigenspace is the set of all eigenvectors plus the zero vector. The eigenspace is the set of just all solutions of this equation, which is the same as this. So going back to our problem, the set of all eigenvalues of A is 1, 2. The set of all eigenvectors of A is this and this, where x2 is any non-zero or real number. And then for each eigenvalue, we have the corresponding eigenspaces. Eigenspace number 1 and eigenspace number 2, where now instead of x2, we can plug in any number, 0 or non-zero. Questions here?
Yeah, so the eigenvector includes the x2s as well, or just the matrix?
No. Eigenvector is the whole construction, x2 times 1, 1. Eigenvector is boldface x.
Okay. And
For
can
lambda
you
is equal to 1, this is a complete description of eigenvectors. And for lambda is equal to 2, this is a complete description of eigenvectors.
and can you re-explain eigenspace then?
Eigenspace is the set of all eigenvectors plus the zero vector.
Okay, gotcha. Thank you.
Mhm.